Hi everyone, and welcome back to the College Physics series. In today's lesson, we're going to be diving into one of the most fundamental concepts in physics, and that is free fall. Before we begin, be sure to download the guided notes that are linked in the description, so that way you can follow along and work through the examples with me. Thank you for being here. Let's get started. So welcome to the lesson on free fall. I want you to grab an object around you. Let's say you're standing up. I want you to grab an object, and I want you to raise it into the air. Let's say it's a ball, a penny, a quarter, a battery, anything. And what I want you to do is that I want you to drop it. What do you think is going to happen? It's obviously going to fall to the floor, right? Or fall to your desk, or fall on your bed. That very basic thing that happens, that is what we call free fall. Easy to understand? Now you know what free fall is. So let's dive a little bit deeper into the detail. Let's say we are standing on a tall building. So you're up here holding an object and you're going to drop it, and it's going to fall off the side of the building all the way towards the ground. It's going to accelerate. Two questions. What do you think happens to the speed as it falls? And does the mass of the rock matter? The second question just refers to, is the same thing going to happen if I have a light rock and maybe some larger rock, where this is a mass M, this is a mass capital M, two different masses? I want you to go ahead and write down your thoughts in the guided notes. So here's the key idea. In free fall, the only force acting on an object is gravity, and all objects, regardless of their mass, accelerate at the same rate when falling, and that is approximately 9.8 meters per second squared. So that's what free fall is. Free fall occurs when the only force acting on an object is gravity. And another key idea for us is that mass does not matter. So it doesn't matter how large or how small an object is. The mass will not affect the rate at which an object accelerates. So the acceleration for the small rock and the big rock are the exact same. Now, before we continue, there are a few important concepts that you need to understand about free fall motion. I'm going to summarize them into 9 points. Here's the first point. The first point is that we use the special symbol g to represent the magnitude of free fall acceleration, where g is equal to 9.8 meters per second squared. Here's the second point. The second point is that g is always positive. Here's the third point. The third point is that g is not the object's acceleration. G is only the magnitude of the acceleration for an object in free fall on the earth. We'll talk about how we define the acceleration, but think about g as just being a property of earth. We will talk about how to define an object's acceleration in free fall in just a moment. Point number 4 is that an object in free fall will have an acceleration ay equals to negative g. But because g is equal to 9.8, as we said up here, then we can write that the acceleration is negative 9.8 meters per second squared. Now this is how we would define an object's acceleration if it were undergoing free fall. We define the acceleration to be negative when an object is in free fall because we typically consider down to be the negative direction. So therefore we get negative 9.8 meters per second squared. Next is the fifth point. So the fifth point is that the velocity versus time graph for an object in free fall will have a slope of negative 9.8 meters per second squared. Remember that the slope of a velocity versus time graph is simply acceleration. The velocity versus time graph for an object under free fall is always going to look like this. Now, there are 3 ways in which an object can be thrown into the air. Number 1, you can drop an object. You can simply let it go, and the graph that you're looking at right here would represent that perfectly because the velocity begins at 0 at the origin. The second way is if you toss something up into the air, maybe like a ball, a football, anything that you throw into the air, you toss it straight up. Well, if the direction of motion is upwards, that's positive, therefore it has a positive velocity. So the graph would be shifted to look at something like this. It starts with some initial velocity and it's slowing down because gravity is pulling it down. The third option is that maybe you're on the top of another building, some height above the ground, and you throw it downwards. So you're at the top and you're throwing something down. Well, if you're throwing it down, the direction of motion is downward, so the velocity is negative to begin with. So all that we would do is that we would shift this line downward to having some initial negative velocity, and the slope would remain the same. And so the velocity versus time graph will have a special shape just for free fall. And of course, you can already imagine the acceleration time graph is just a horizontal line at negative 9.8. Moving on to number 6. The sixth point is that g is not gravity. G is the free fall acceleration. I know the letter G starts with the same letter as gravity, and the free fall acceleration is due to gravity, but they are two completely different things. Gravity is a force, as we will learn later on, but the G that I'm talking about in this lesson is the G that represents free fall acceleration. The one I'm talking about is measured in meters per second squared. The gravity that I do not want you to confuse it with is measured in newtons. Completely separate ideas, although related, but do not confuse G for standing for gravity. G is a property of the Earth, and its value is 9.8 meters per second squared, always positive. The next idea, key idea number 7, is that G equals 9.8 meters per second squared is only valid for Earth. Remember, G is a property of Earth. All other planets have different values of G. On other planets, you will find a different value for the free fall acceleration. Key idea number 8. Idea number 8 says we can describe the acceleration of any object in terms of G, where 1 G is equal to 9.8 meters per second squared. In future examples, we're going to want to see how many G's a certain acceleration is for some type of object. Maybe it could be a plane before it takes off. If you've ever been on a plane, the planes speed up quite quickly in order to fly into the air, in order to get off the ground. And so we can ask ourselves, how many G's is that? How does it compare to the free fall acceleration on Earth? If I want to figure out how many G's this acceleration is, then all that I have to do is divide my acceleration by 9.8 meters per second squared. In this case, when I divide the numbers out, it's 2. And when I divide by 9.8, I automatically get my answer in G's. It is 2 times the free fall acceleration on Earth. So in the future, we'll have examples that ask for how many G's is this acceleration. The last point, number 9. Number 9 says, in the absence of air resistance, all objects will accelerate at 9.8 meters per second squared toward the center of Earth, regardless of mass. And another reason why I mention this is because at the very beginning, I asked you to drop any object around you. And maybe that was a sheet of paper. And if you compare a pencil with a sheet of paper, you might notice that the papers will float down towards the floor or whatever surface that you're on. And that is because the paper is not technically in free fall. Technically, nothing is in free fall because we do not live in a vacuum. There is air resistance everywhere. But for more massive objects, we can sort of neglect the effects of air resistance. But in the case of the paper, since it's so large, it has a large area, then the effect of air resistance is much greater. Therefore, it falls slowly. If you were to go to a place that had no air resistance, and you took that paper and that same pencil and you dropped them, they would accelerate or they would fall at the exact same rate. Now, there's one last thing I want us to talk about before we get into some examples. Just to reiterate, these 9 ideas are very fundamental for your understanding of free fall. And so we're going to be practicing a little bit with these ideas. But before we do, I want to touch again on the evolution of our big 3 kinematic equations of constant acceleration motion. Let me show you the original version in which I wrote. Now, I gave you the kinematic equations looking like this, but as we saw in the last video, these equations are very bare. They hold very minimal information. When we saw an object that experienced 2 different types of motion, this format was not very useful for us, and we needed to add subscripts. So that is what we're going to be utilizing from now on. So I gave you a version that looked a little more like this, and I will write it in the vertical form. What you're looking at here is a much more descriptive version of the exact same equation. Let's take a look at the first one. I have a V here, a V there. They both stand for velocity. I have an F and I have an F. They both represent final. But I have included an extra Y, and that Y tells me the direction in which this equation is being applied to. So if you see the equation in this form and you see Y's, you know already that this equation is being used for some vertical motion. And the same thing applies for the rest of the equation. The YF, vertical position, final. Initial vertical position. AY, that represents vertical acceleration. If you saw AX, that would be horizontal acceleration. But now we have a special case where AY is equal to minus G. So we can rewrite these kinematic equations specifically for free fall. Now, you don't need to look at it this way. You can always start with these 3 and then adjust in the moment for free fall. Let me show you what the equations would look like if we were to plug in negative G for AY. So this is how the kinematic equations are going to look when we are specifically talking about free fall. This is the free fall version of the big 3 kinematic equation. If you notice, notice when we plugged in ay to be negative g, the negative already accounts for the motion. The motion is down. That's why instead of the plus signs right here, we see minus sign instead of these pluses. So those already account for the direction. And then of course the value of acceleration itself is just g, and we know that g is just 9.8 meters per second squared. So it kind of simplifies things specifically for free fall, but again, you can always just start off with this and modify in the moment if necessary. So that way you don't need to memorize a whole other set of equations. This set of equations for free fall is just a special case. So now that we've talked a lot about the theoretical background of free fall, let's go ahead and do a few examples. So we're going to begin with a conceptual example, and it reads, imagine a ball thrown upward at 19.6 meters per second. What happens as the ball rises and falls back down? First, as the ball rises, gravity is still acting on it, pulling it downward. So even though the ball is moving upward, its velocity is decreasing because gravity is slowing it down by 9.8 meters per second every second. So let's sort of draw what that looks like. So the ball is thrown upwards from this point. And so I can draw that as a motion diagram right here. So at that point, it's moving 19.6 meters per second upwards. So what's going to happen is that this thing is going to come up and then it's going to come back down. You're throwing it just straight up. So here we're at 19.6 meters per second upward. So at this next point, I'm at 9.8 meters per second because the velocity is changing by 9.8 meters per second every second because that's the acceleration due to gravity. And then I come up one more point and I'm at 0. For every second that the ball goes up, you need to subtract 9.8 from its velocity. So at the peak, it's going to be motionless. At the peak of its motion, the ball's velocity comes to 0 for a split second, but gravity does not stop acting on it. After that, the ball begins to fall back down and its velocity increases again in the downward direction. So if I were to represent that over here, I start from 0 and the next second I gain 9.8. So here I'm gaining 9.8 meters per second. Let me not include a plus sign, but it's gained. And then during the next second, I gain another 9.8. So I get 19.6 meters per second. So going upwards, you lose. At the very peak, you're at 0. And once you pass the 0, as you move downwards, you're gaining. But the velocity is going down is obviously negative because downward is the negative direction. By the time the ball reaches the point where it was thrown, its speed will be the same as when it was thrown, which is 19.6 meters per second, just in the opposite direction. This is sort of a property of symmetry when it comes to the trajectory of the particle or the trajectory of the object. So here we have a half circle, and this half of a circle is going to represent an object that's being tossed up into the air. The properties that we've learned so far is that at the very peak of the motion, the velocity is 0. But if I take a straight line and I cross it through any 2 points, this point and this point will have the exact same speed. Let's just pretend it's 9.8. Going up, it will be positive, but coming back down, it will be negative. If I do another line, these 2 points right here will have the exact same speed, but will be opposite in direction. So let's just add another 9.8 to be 19.6 meters per second. This will be negative 19.6. And let's say this is the point where it initially started, and let's say you add another 9.8, and that will be 29.4 meters per second. But coming back down will be negative 29.4. Later on, we're going to be taking advantage of this type of symmetry that's very special to freefall. It'll make our problems a lot easier to analyze. So to summarize for this conceptual example, when the ball rises, it slows. And then at the peak, it is motionless. Finally, when it falls, it speeds up. And the entire time, the acceleration is pointing downward. At this point, acceleration is the same. Over here at any of these points falling down, the acceleration is the same. Throughout this entire changing process, acceleration has remained constant the entire time. Hence, constant acceleration motion. But the value of the acceleration is what's so special, and it belongs to the Earth. Now let's work through a real-world example to apply our equation. Okay, so here's our example, and it says a stone is dropped from a height of 60 meters. How long does it take to hit the ground, and what is its velocity just before impact? Now, as we mentioned in the previous video, it would be best to draw a picture so that way we understand what's going on in this example. So my step one, I'm going to draw my picture. So here's what's happening. Let's say we have a little bit of a cliff. What I'm doing is that I'm dropping a stone, or up here is where I'm going to find my initial vertical position, my initial velocity, and my initial time. The stone's going to fall all the way to the ground. That's what we're going to call 0 meters, height of 0 meters. And it's at this point at the end of the motion, so I find my final vertical position, my final velocity, and my final time. So that is what's happening in this picture. My second step is to write out my knowns and unknowns. It reads a stone is dropped. When something is dropped, it's the same thing as when we used to read that an object starts from rest. Dropped means that my initial vertical velocity is 0 meters per second. It's dropped from a height of 60 meters. That means that my initial vertical position is 60 meters. Bouncing off of that, I know that my final position is going to be 0 meters. So I can use these two pieces to then get my vertical displacement, which is just final minus initial. In this case, the final is 0 meters minus 60 meters because that's my initial. So altogether, my delta y is going to be negative 60 meters. That makes sense. Displacement is a vector quantity, and the direction in which the object was displaced is downward. So I do expect a negative answer for my displacement. So altogether, I'm going to erase this and just simply put that my displacement is negative. Next, it says, how long does it take to hit the ground? That is a question of how much time it took. And next, what is its velocity just before impact? So I'm looking for my final velocity in this case. Here are some things that are not mentioned, but that I should apply by using logic around this situation. I know that this object is only under the influence of gravity as soon as it leaves our fingertips. As soon as we drop something, you need to release your fingers, your grasp on any object, and then it's going to fall because the earth is going to pull on it. So because there's nothing else affecting this object besides gravity, then we say this object is in free fall. And when you do say that an object is in free fall, then we can define the acceleration to be minus g. So that's something that we need to apply to the situation now that we understand it. Step 3, we are going to choose the right equation. So let's go ahead and bring out the big three kinematic equations. So these are the three equations that we wrote down specifically for free fall motion. So let's go and check off our knowns and unknowns. VYF, I want to figure that out. I know the initial velocity, I know the value of g, and I'm looking for the time. So there are two unknowns in that first equation, so therefore I cannot use that one. I know my final and my initial positions. I know my initial velocity. I'm looking for time. I know my free fall acceleration, and I'm looking for my time. Again, two unknown. Final velocity, I'm looking for that. My initial, I know my free fall acceleration, and I know my vertical displacement. Therefore, I can use only the third equation to solve for VYF. And once I accomplish that, then I'll be able to take the question mark off of this one, and then I'll be able to use this equation to solve for the time. So in this case, there is a specific order. I must first use the bottom equation to solve for the final velocity. So let's go ahead and do that. So luckily in this case, when we're coming to step 4 to solve the equation symbolically, well, it's already almost solved because I'm looking for VYF, not VYF squared. So what I'm going to have to do is that I'm going to have to take the square root of both sides. So on the left-hand side, it's going to cancel only when I consider both solutions for a square root. So under the radical, I'm going to get the initial velocity squared minus 2g delta y. So now that it's solved for symbolically, I can go ahead and plug in my numbers. Luckily, my initial velocity is 0, so I can rewrite it like this before I plug in my numbers. So it's going to be plus or minus square root of negative 2g delta y. So I can go ahead and plug in my values. So I'm going to get plus or minus square root negative 2. G is just positive 9.8 meters per second squared. And my delta y is negative 60 meters. Luckily for me, I have two negatives under the radical because a negative times a negative is just a positive. And I can only take square roots of positive numbers. I cannot get imaginary values for the final velocity because that would not make any sense. If you are trying to take the square root of a negative number when calculating for time, displacement, velocity, anything, then you need to recheck your work. What I'm going to get here is I'm going to get plus or minus the square root of 1,176 meters squared per second squared. How do I know that? This meter is in the numerator, so is this one. So they multiply to become meter squared. And then I have the second squared already in the denominator. So when I take the square root of 1,176, I'm going to get 34.3. But if I take the square root of meter squared, I just get meters. If I take the square root of second squared, I just get seconds. And I do measure velocities in meters per second. So that's how I know that things are going well for me mathematically in this problem. So since we're following the math here, I get two answers. I get a plus or minus. But physically, what's happening in the scenario, there's only one thing happening. An object's just falling. So this is where you need to be a bit mathematically inclined to reason through which solution applies best to your problem. So does the positive root better describe my final velocity? Is it a positive 34.3 meters per second? Or is it a negative? Remember, in physics, we use positives and negatives to define directions. And so, since this object is moving moving down, the negative root is going to better describe my physical scenario. So negative 34.3 meters per second will be the answer for that first part. And that's simply because the object is falling downward. So now my VYF is known. The last part is I'm going to solve for the delta t using the first equation. So luckily this VYI is 0, so I can simplify my equation a little bit more. On the right hand side, I have negative g times delta t, and I'm going to undo that by just dividing by negative g. What that'll do is that it'll cancel the g's, cancel out the negatives, and I'll just get that the time interval delta t is equal to the final velocity divided by negative g. I just found that my final velocity was negative 34.3 meters per second, and my negative g is negative 9.8 meters per second squared. Notice, if my value for the final velocity were positive, if I had chosen this positive answer, or if I had chosen positive root, then it would be up here as well. A positive divided by a negative is a negative. I cannot get a negative time interval. That does not make any physical sense. So this is another way I can check that my answer initially was correct. Using the calculator, I'm going to get a time interval of 3.5 seconds. I've already talked about how to simplify the units, so I'm not going to go over that anymore. And that'll complete this example on finding the time it takes for an object in freefall to reach the ground and its velocity just before impact. I have one more challenging example for us, and let's take a look at it. So our slightly more challenging example reads, you throw a ball downward from the top of a 50-meter building with an initial speed of 10 meters per second. How long does it take to hit the ground? This one may not look so challenging, and probably because it's not really. Our first step is to break down the scenario by drawing a picture. So my picture is going to look very similar to last time. We have a person, but this time this person is throwing something down with a non-zero initial velocity. So again, up here I find my initial vertical position, I find my initial velocity, which in this case is not zero. Here's my initial time, and it's going to hit the ground, and that's where I'll find my final position, my final velocity, and my final time. Step 2 for my knowns and unknowns says we throw a ball downward from the top of a 50-meter building. So because the initial is 50 meters up, the final is 0, I know that my delta y is going to be negative 50 meters. And we throw that ball with an initial speed of 10 meters per second. Notice how it says speed. How do I convert that into a velocity? Well, you need to remember that velocity is just a magnitude, a speed with direction. So my initial velocity, the speed is 10 meters per second, but the direction is downward. So we're going to call it negative 10 meters per second. The question is just simply asking for the time. So I'm looking for the time interval. Now, if I just read the question, I'm able to get those pieces of information, but I need to apply a little bit more to the situation. I need to apply the fact that I know this object is in free fall, and any object in free fall is going to have an acceleration of negative g. My next step is to choose the appropriate equation. So let's go through our equations and see which one is going to work best. I know my delta y's. I know g, this object is undergoing free fall acceleration. My delta t's is what I'm looking for. I know my vyi, and I do not know my vys. If you notice, all of the equations with time have two unknowns, except for this one. In this third equation, I could solve for the final velocity. Like the way I did in the previous example, I could first find my final velocity and then plug my final velocity back over here. But we saw that that took 2 steps. And what I'm about to show you is that you can actually solve this equation in just a single step. And we can solve this equation in a simple step using the second formula. I'm not going to explain why right now, but I want you to discover the pattern for yourself. So I'm going to first write out the second equation. And I know that I usually recommend to solve this symbolically, but you're going to find this is going to be pretty tough to solve symbolically. It's possible, but it's tough. And we're going to use a shortcut. But you can only see what the shortcut is if you plug in the numbers first. Well, it's not impossible. It's much easier to see the shortcut if you plug in the numbers first. So let's go ahead and do that. My final position is 0. And also, to make this clear, I'm going to not write the units, even though it's a best practice to write the units. I'm just going to write the numbers for now. That way you can see the pattern. The initial position was 50 meters. My initial velocity was minus 10 multiplied by delta t minus, and then I have half of 9.8, sorry, no units for now, multiplied by my delta t squared. Let's simplify this a little bit more. Now I'm going to write this in a way that may look familiar. Does this format look familiar to you? Some of you may be scratching your head saying, what is this guy talking about? Some of you may be realizing that this is the form of a quadratic. Ax squared plus bx plus c is equal to 0, where the variable is just my time, my delta t. The c is 50, the b is negative 10, and the a is negative 4.9. Those are the coefficients. So if this equation that I've written out is in the form of a quadratic, and you can solve any quadratic by using the quadratic formula. Now, some of you may think this is slightly more difficult than just solving the final velocity and then plugging it into the other equation. You can choose to solve this however you wish. But I want to show you this solution so that way whenever you come across another problem similar to this, you have the skills to be able to solve it using the quadratic formula. So in order for us to use a quadratic formula in this example, you need to identify what your A, B, and C are. I already wrote it out for you. The value of A is negative 4.9, the value of B is negative 10, the value of C is 50. And all that I'm going to do is that I'm going to plug in these numbers into my quadratic formula and then let it simplify on its own. The second thing I'm going to modify is that the x, that is in ax squared plus bx plus c equals to 0, for our purpose it's a delta t. We're trying to get the time. So instead of the x, I'm going to put the delta t. So this time when I'm plugging in my a, b, and c, I'm going to include the units. That way I know that my final answer has the right dimension. So delta t equals negative b. B is already negative 10, so if I make it a negative of a negative, will be a positive. So I'm going to get 10 meters per second plus or minus the square root of b squared, negative 10 meters per second squared, minus 4 times a, that is negative 4.9 meters per second squared, times c, which is 50 meters. And all of this is divided by 2 times a, which is negative 4.9 meters per second squared. Now, this may look hideous, but it's actually not that bad. Let's go ahead and simplify the radicand. So I get my 10 meters per second plus or minus the square root, negative 10 meters per second squared. Negative 10 times negative 10 is 100. Meters per second multiplied by itself is meters squared per second squared. Now, here I come to the minus 4 times negative 4.9. Here I get a negative times a negative, so I'm going to get a positive. When I multiply all of the numbers out, I'm going to get 980. I have a meters in the numerator and meters in the numerator, so it's going to be meters squared per second squared. And everything again divided by 2 times a, which in this case would be negative 9.8 meters per second squared. Let's continue along. I get 10 meters per second plus or minus. Under the radical, I'm going to get 1080. 1080 meters squared per second squared, all divided by negative 9.8. Now, what I'm going to do is that I'm going to simplify the square root of 1080 into simplest form using a radical. Simply because using a radical, it will be neater for our calculations so that way we can avoid rounding throughout this process. That way we get the most accurate answer. So I can reduce 1080 into 10 and 108. I can reduce 10 to 5 times 2. I can reduce 108 to 2 times 54. I can then reduce 54 to 6 times 9, which 9 will be 3 times 3, 6 will be 3 times 2. So the idea here is that if I get a pair, I get to bring it outside the radical. My first pair is 2 and 2, so it goes outside the radical. My next pair, 3 and 3, so it gets multiplied outside the radical. Now I have 2, 3, and 5. Those do not have a pair, so therefore they belong back inside the radical. 2 times 3 times 5. So the square root of 1080 can also be rewritten as 2 times 3 on the outside is 6, 5 times 3 is 15, times 2 is 30, 6 square root of 30. So that's how I'm going to simplify the square root of 1080. So in my equation, my delta t becomes 10 meters per second plus or minus 6 square root of 30. And then, so that's me taking the square root of 1080, but I also need to take the square root of the units. That'll just be meters per second, all divided by negative 9.8 meters per second squared. Now, because I have this plus or minus right there, shining right into my eyes, saying hello, wants to be noticed, what I have to do is break this apart into 2 separate solutions. I'm going to write out one version where I use the plus sign and then the other version where I use the minus sign. So I'm going to get delta t equals 10 meters per second plus 6 square root 30 meters per second divided by negative 9.8 meters per second squared. I'm going to call this delta t1, and then I'm going to have another version where I'm going to use the minus sign, and I'm going to need to see which one will be a better fit for this situation. So let's look at delta t1. Let's analyze it. In the numerator, I have a positive 10, and then I have a positive 6 square root 30, which is a positive number. So in the numerator, I'm going to get a positive number, and in the denominator, I'm going to get a negative. What that is going to output is a negative answer. Can I get a negative value of time? I don't know what negative time means, so this version will be inappropriate for my solution. The answer for how much time it takes for the object to fall is not a negative answer. So this makes no physical sense. Therefore, I have to trust that I've done everything right with delta t2. So I'm going to get 10 meters per second, and I'm going to subtract it by 6 square root 30. And in the calculator, you should get negative 22.86 meters per second. That is perfect. I definitely need a negative answer in the numerator because when I divide it by the negative answer in the denominator, so the calculator will output a number of 2.33 seconds. So seconds is what comes out of this and those units being divided out. So my delta t2 answer will be 2.33 seconds. And that will answer how much time it took for this ball to fall down from a roof with an initial speed. Now it is your turn. Here's a problem for you to solve on your own. So here is the try it yourself problem. It reads, a ball is thrown upward with an initial velocity of 12 meters per second second from a height of 20 meters. How long will it take the ball to hit the ground, and what will its final velocity be? Leave your answers in the comments below and I'll be sure to check them out. And that's going to wrap up our lesson on freefall. Today we learned that all objects, regardless of mass, fall with the same acceleration due to gravity. We also explored how this acceleration affects the motion of objects, whether they're moving upward, downward, or drop from rest. If you found this lesson helpful, please consider liking the video, subscribing to the channel, and sharing it with others who might benefit from it. Also, don't forget to leave your answers to the practice problem in the comments. I'd love to see how y'all did. Thank you for watching and being a part of the College Physics series. I look forward to seeing you in the next lesson.